Welcome to the Polynomials channel, season 3, episode 37, the episode which I titled Sine as an Infinite Product and its 3 applications, because in this episode we will decompose the trigonometric function of sine into an infinite product, and then we will look at 3 straightforward applications of that decomposition, and namely these applications will be the so-called Wallis formula for the number pi, then the decomposition of the sister function of cosine into the corresponding infinite product, and the so-called reflection formula for the gamma function. But before we deep dive into the underlying, mostly real analysis of this problem, as a traditional and friendly reminder, if you're joining our channel mid-season, then first of all, thank you very much for your vote of confidence. Thank you for subscribing to our channel and welcome to our channel. And second of all, perhaps the most efficient way for you to gain the most academic benefit from working with the material that we present on this channel is for you to go to the home page of our channel, and at the top of that page in the channel's trailer section, find the episode titled The Polynomials Channel How To. We recommend that you watch that episode in its entirety, follow all the instructions that we give in that episode, because in that episode we explain and motivate everything that we do on this channel. If you have any questions, then by all means do ask. The best way for you to ask your question is to find an episode on this channel that is of interest to you and use the comment section under that episode, and I will take it from there. And of course, and as usual, I would like to extend my deepest gratitude to all the current subscribers and the current supporters of our channel. In the mathematical problem S3E37, we're asked to show that for all real numbers x, which are measured in radians and which are distinct from integral multiples of pi, the following decomposition of the trigonometric function of sine into an infinite product holds. The trigonometric function of sine evaluated at the argument x measured in radians can be represented as the product of the argument itself, x, and an infinite product whose common term has the following structure: 1 minus the ratio of x raised to the second power divided by n squared times pi squared, where the dummy multiplication variable n varies from 1 to positive infinity. And usually on this channel, when I present a solution, I write along as I develop that solution, but because in this particular problem there will be a very large amount of writing involved, I will pre-write the results of the solution of the problem on the board prior, and then I'll go over it with you in greater detail. Strategically, in the proof that we're about to construct, we will use the idea that a certain advantageous polynomial, according to the fundamental theorem of algebra, can be decomposed into a product of terms that are linear in the roots of such a polynomial, and that is essentially where the upcoming decomposition of the trigonometric function of sine will be coming from. Tactically, however, we will carry out the strategic idea or the strategic agenda as follows. Recall that according to the so-called de Moivre's identity or de Moivre's formula, for all theta real measured in radians and for all integral values of m, which are negative whole numbers, 0 and positive whole numbers, the following identity follows. Geometrically, any point taken on the origin center unit circle, and algebraically such a point has the following incarnation: cosine of our real number, theta plus I, the imaginary unit, times sine of the same angle theta raised to the integral power m, can be represented as the sum of the following two terms only: cosine of the argument, that is a integral multiple of the original function, theta m times theta plus I, times the trigonometric function of sine evaluated at the integral multiple of the angle theta. This is the step number one. Step number two is to turn things around and apply the binomial theorem decomposition to this sum right here, since we have this nice integral power. And according to the binomial theorem, our sum sigma can be represented as the product of the following four terms: the binomial coefficient m choose k times the trigonometric function of cosine from de Moivre's formula raised to the power m minus k. K over here in this case is the dummy summation variable that changes its values from 0 to m, times the imaginary unit I raised to the power of k times the trigonometric function of sine evaluated at the argument theta raised to the power of k. And here the idea is to massage this sum more thoroughly and see what kind of material this sum will generate. And the next segment is optional if you already know how to handle the imaginary unit. If you, for example, know that I is a generator of a finite multiplicative commutative group of the fourth roots of unity, you can skip the next segment. In the study of high algebra, you will learn that the imaginary unit I is a generator of a finite commutative multiplicative group of the fourth roots of unity, sometimes designated as U4. It has the following four elements: positive unity, positive imaginary unit, negative imaginary unit. And that is why this group is finite. The group is commutative because complex numbers commute under multiplication. The product of any two complex numbers z1 times z2 is equal to the product of the number z2 times z1 taken in reverse order. And essentially, in some sort of grotesque statement, this is the entire theory of groups for you in one sentence. That means that the elements of this set form a algebraic structure called a group under the operation of multiplication, and that means that such an operation must be associative, and no matter how the elements of a set under consideration interact with each other pairwise through the given associative operation, then another element of the same set is produced, and this is the case over here. So not only the product of the imaginary unit I with itself produces an element of the group, but it turns out that the imaginary unit I has enough juice to enumerate all the elements in that set without exception. And I wrote this multiplication table for you, if you will, over here in this line of symbols. I raised to the 0th power is 1, I raised to the first power is itself, I squared is -1, I cubed is -I, and the interesting thing over here that in the old days, this particular characteristic of a group element was called the period. These days it's called the order. So the order of the element I is 4, which means that this multiplication table repeats itself forever and ever with the period of 4. And eventually, of course, you will be doing this in your mind algebraically, but initially it pays to understand a geometric motivation, or in some sense, a geometric demonstration of the multiplicative behavior of the imaginary unit I when that unit is raised to, let's say, positive or non-negative integral powers. I captured this behavior over here on the right side of your screen, and here is the lowdown. Usually raising any number to any power cannot be thought of that way, but when that power is integral and positive, then it is possible and permissible to think about raising a number to an integral power as a consecutive multiplication. That's defect number 1. This is defect number 2, multiplication, the algebraic multiplication of any complex number by I geometrically corresponds to the rotation of that, let's say, non-zero complex number about origin counterclockwise by pi over 2 radians, because pi over 2 is precisely the principal argument of the imaginary unit I taken with the plus sign, and consequently that means that we multiply the imaginary unit with itself. We're simply rotating the point that is distant 1 unit away from the origin along the periphery of the origin centered unit circle counterclockwise. And this sort of visual multiplication table is captured over here, and the meaning of this table is the following: when I is raised to any integral power, positive integral power, that starts with 1 and then steps with the period of 4. That means these powers run as 1, 5, 9, 13, 17, 21, 25, 29, and so on. We will always produce the imaginary unit itself, I. Furthermore, if we start raising that number to the even powers starting with 2, and then again stepping with the period of 4 along the proverbial whole number line, then we will have the following powers: 2, 6, 10, 14, 18, 22, 26, 30, 34, and so on. And we will always produce -1 in this case forever and ever. Next, if we raise I to the even power that starts with 3 and also steps along the proverbial whole number line with the period of 4, and that means the numbers 3, 7, 11, 15, 19, 23, 27, 31, and so on, will always produce -I. They will put us on the negative branch of the imaginary axis. And lastly, when the imaginary unit I is raised to the power, to the even powers 4, and then chugged along with the steps of 4, that is 8, 12, 16, 20, 24, 28, 32, and so on. This will put us back onto the positive unity. And in some sense, this is the algebra of the multiplicative group of fourth roots of unity captured on the left. And this is its visual representation. So by basically cranking the number I with quarter turns every time there is a power that we come across with, this is what essentially happens geometrically. And once you understand the geometry of the multiplication of I by itself certain number of times, then it should be no mystery for you to figure out what is going on with our binomially expanded left-hand side of the de Moivre's formula. And here the situation is the following. Again, you can drill down. This is like super elementary theory of numbers, because here these numbers will be generated. For example, these odd numbers are generated by which form? The old odd numbers can be represented as 2 times q plus 1, but in this case the q is what? The q is even. For 1 it will be, we can say, let's say -1. For 5 it will be 2. 2 times 2 is 4 plus 1, 5. For 9 it will be what? 4. 2 times 4 is 8 plus 1, 9. For 13 it will be what? It will be 6, and so on. And in this way you can analyze all the numbers over here. Here we have the same situation, but this time such an even number will be represented which way? 2 times q. And over here you can see that q is what? The q is odd. 1 for 2, 3 for 6, 5 for 2, 7 for 14, and so on. Likewise, you can decompose these numbers over here also, as well as 2 times q plus 1, or maybe -1, depending again on how you want to analyze the situation. But fundamentally, essentially, this is what is going on. And we can now understand that when our imaginary unit I in the binomial expansion of the left-hand side of the de Moivre's formula is raised to the power of k, and k is a number that is even or representable as 2 times q for a suitable integer q, then according to the way in which powers are manipulated, we can raise just I to the second power and then the whole thing to the qth. We know that I squared is -1. 2 turns, 1, 2. Here we go, -1 raised to the power q. And again, this is where the parity of these numbers, q, 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 and q, will dictate the outcome of this particular power. So we'll have -1 raised to the power of q in this representation of k, and this splits into positive unity and negative unity. So in other words, this term will always flip-flop between +1, -1, +1, -1. There will be no I in this expansion of the imaginary unit I itself. You can see that geometrically this imaginary unit sort of dissolves into positive unity or negative unity. The same thing happens when the power k of the imaginary unit I in our expansion is odd or representable as 2 times q plus 1, let's say, where q is a suitable integer. Here we partition this expression as I times I raised to the power of q. You know what happens in this case, so we already can skip it down right away. Have minus 1 raised to the power of q, but it is important that one copy of I is always there. So that means that depending on the parity of q, this q and this q right here, our power I raised to the power of k, which is odd, will always flip-flop between what? It will flip-flop between positive I and negative I, plus I minus I, plus I minus I. And what does that mean? That means that technically for us, all the material in this mysterious looking sum, you can write it down by yourself. This is not too complicated. It's just tedious manipulation of the binomial coefficients, m choose k, then the integral powers of m, the result of raising the imaginary unit I to an integral power k, which I explained over here, correspondingly sine expanded. But fundamentally behind all this tactical maneuvering, keep one big picture in mind. All the material, all the terms in this expansion of the sum sigma shown over here can be partitioned into two distinct and non-intersecting piles. In one such pile, we will have the I-free terms, or terms which do not have I as one of its factors. And the other such pile will be the I-bound terms, in other words, all the terms that have precisely one copy of I attached to them. And the fact that these two piles do not intersect means that the I-free terms are not in the I-bound pile, and conversely, the I-bound terms are not in the I-free pile. So in other words, we can, once we write down this sum, once we expand it on paper, I suggest here that you do it with some specific number. Pick, for example, m, I don't know, 5, 6, 7. Try it with different relatively large but not so large numbers to see how these things play out. But for us, that means that all the material in this expansion over here can be put into the shape that mimics the right-hand side of the de Moivre's formula. And for us, that means the following. Recall that two complex numbers, z1 and z2, equal one another. z1 equal to x1 plus I times I1, and z2 equal to x2 plus I times y2, if and only if their real parts match. x1 is equal to x2, and separately and at the same time their imaginary parts, y1 and y2, match also. And that means that for the reasons that we explained in the previous segment a few seconds ago, all the elements of the sum sigma associated with the dummy summation variable that is even will go where? Will go into the cosine pile. Will go into the cosine pile because this is the real part of the right-hand side, or the real part of the complex number that sits on the right-hand side of the de Moivre's identity. And all these terms are shown over here, and likewise all the summands of the sum sigma that are associated with the dummy summation variable being a number that is odd will go into the sine pile, because sine over here on the right hand side is the imaginary part of the corresponding real number. And intuitively it is okay, or it is possible to just remember in general from the bird's eye view or 1,000-mile view that with the cosine, the expansion of the cosine into the corresponding summands, it is the show of even numbers, 2, 2, 4, 4. Here we have 0 and 0 and so on. And the trigonometric function of sine is associated with the odd show of powers, 1 and 1, 3 and 3, 5 and 5, 2k minus 1, 2k plus 1, and so on. So in order to save me some space, because these things, even when you use paper, with pen and paper, these things tend to be very long. You need quite a bit of real estate to write this down. For the brevity's sake, we will designate the cosine evaluated at the angle theta, not the multiple not the multiple copies of the angle theta, but single copy, single angle theta as lowercase c, the trigonometric function of sine evaluated at the angle theta. One copy will be lowercase s, so you can see yellow stands for cosine, yellow C stands for cosine, blue S stands for sine, purely for the sake of brevity. And in some sense, we do not really need to write all these trigonometric functions because we will use them as a material, as the fodder for our sculpting of the underlying polynomial. And the structure of the expansion of the cosine over here is the following. Remember, we have the show of even numbers, so all the binomial coefficients over here will be m. Choose what? M, choose an even number. 0, 2, 4, 6, 8, 10, 12, and so on. M2, and the corresponding power of the trigonometric function of cosine will also be m minus that even number. Here it's m minus 0, m minus 2, m minus 4, m minus 6, and so on. The corresponding powers of sine will be also even. Don't forget, here even number for the sine is what? 0. Here it's 2, 4, 6, 8, and so on. This over here in the middle, I showed you the structure of the general term. If you were to write down the sum in its compressed form in the way that I wrote over here, usually if you have enough experience working with the sums, you already can see what is going on. But initially, in order to develop a better feel, I recommend that you actually, as I mentioned before, go ahead and write down, do not be lazy, write down 4, 5, 6, 7, 10, 20 expansions just to get the feel for it, because the great minds of the past, for example, Carl Gauss or Leonard Euler, they used to run these computations just for fun to see how things work. And this is how you develop the feel, how you develop a special personal rapport with the material that you work on. This is the common term. Now, once we get down to the last term, this is usually a very pesky situation to deal with. In many textbooks, you do not even see the last terms. All you see is the ellipses, but on this channel, we do our due diligence. And the last term, this is the last term. Look at this on the right-hand side. Here is the last term. This is the final frontier, so to speak. The last term, remember, splits into two choices, when m, the power into which we expand our Demoivre's identity, is even, or is representable as 2 times k. Then we have this term over here, negative 1 raised to the power m over 2 times the trigonometric function of sine raised to the power of m. In this case, remember the show of even powers. Here the cosine starts with m, but sine starts with 0, the power 0, and then they crisscross. The power of cosine diminishes in even steps, and the power of sine increases in even steps. So eventually, in the last term, when m is even, what do we have? Cosine raised to the 0's power. So here explicitly it is absent. Now, when m is even, when m is odd, representable as 2q plus 1, then the structure of the last term will be the following: minus 1 raised to the power of m minus 1 over 2. M minus 1 in this case is guaranteed to be even, divisible by 2, and then we have m cosine raised to the first power and sine raised to the power of m minus 1 over 2 again. This number will be an integer. So this takes care of cosine. And now let's talk about the sine. Essentially, the structure again is the same, but remember, with sine, it's the show of odd powers or odd numbers. So all the binomial coefficients in the expansion of sine will be m, choose an odd integer: 1, 3, 5, 7, 9, 11, 13, and so on. Consequently, the powers of the trigonometric function of cosine and sine will, of course, sum to m, but this summation will be done by splitting these powers into the odd shaped components. So we have m minus 1 for the first term, s raised to the first power. For the second term, we have cosine raised to the power m minus 3. 3 is an odd number. And then the sine, the trigonometric function of sine raised to the power of 3. The next coefficient, binomial coefficient, will be m, choose 5. Cosine will be raised to the power m minus 5. 5 is odd again. the trigonometric function of sine raised to the fifth power. 5 is odd. Again, they sum the powers of cosine and sine, sum to m, minus 5 and 5, and so on. Now, this again will be a common term. If you were to write down the sum in the compressed form using the summation notation, this is what you will write. Over here it was 1 minus 1 raised to the power of k minus 1 raised to the power of k. Where did this minus 1 come from? Well, we explained. I is a generator, multiplicative group of fourth roots of unity, commutative, geometry, rotation about the periphery of the origin center unit circle. You understand how these powers flip-flop. Plus 1, minus 1, plus I minus y, but minus I, but essentially minus 1 is there. Now, the binomial coefficient over here, m, choose 2k plus 1 for the sine. For the cosine is m choose 2k. I'm sorry, I missed it over here. And times the trigonometric function of cosine raised to the power m minus 2k minus 1. Sine is raised to the power 2k plus 1. And more terms like this. And what does the last term will look like? The last term will look as follows. Again, when m is a number that is even or representable as 2 times q for a suitable integer q, we will have negative 1 raised to the power m minus 2 over 2 times m times cosine raised to the first power times sine, the trigonometric function of sine raised to the power f to m minus 1. And when m is odd or representable as 2q plus 1 for a suitable integer q, we will have the following structure of the last term. Minus 1 raised to the power m minus 1 over 2 times the trigonometric function of sine raised to the power of m. And the reason I'm going so thoroughly about these decompositions and the mechanics of how we produce the material that we will work on in the future is 2 reasons. First of all, we understand so that everyone in the audience understands where did it come from. And reason number 2 is I want to create an argument that is templatizable, an argument that you can use to craft your own results, which will be different from our expansion of the trigonometric function of sine over here. You can use these expansions and this reasoning as a template, for example, for the construction of the corresponding results for the trigonometric functions of tangent and cotangent. But now that we understand where did this material come from, we can start working on sculpting our polynomial in earnest. At the beginning of the previous segment, you saw several sample expansions of the trigonometric function of sine and cosine in both cases, when the number m is even, when the number m is odd. And even though I came up and I constructed these expressions for you, it is always a good idea for you to do the same constructions yourself again in order to develop the better understanding of the material and put the good sense of what's going on into your fingers, if you will. So now, again, in the previous segment, I made a mistake with the expansion with the common term of the cosine. Remember, it was the common term was m choose 2k, because with the trigonometric function of cosine, it is the show of even integers, even, so m over 2k, the generic term. Make sure that you do not miss that. And in the expansion of the trigonometric function of sine, it is the show of odd integers, so m choose 2k plus 1 is the main character of this expansion. And because we already covered the exact shape of the last, this is usually, like I said before, it's a pesky situation, pesky terms, they flip-flop in interesting ways. But because I covered the explicit shape of the last term in either expansion, I will take the luxury of now writing down the ellipses, because you know what's hiding behind these ellipses. The last terms are covered in both cases explicitly. So now, to save some time in real estate, I will not do it. But again, it is important here to pay attention to the quality of the powers of our expansions. These coefficients, in some sense, are not interesting to us right now. But in general, in other types of problems, for example, when we evaluate certain finite trigonometric sums, the values of these coefficients in front of these products will be very important. And this is actually one way to construct the binomial sums. You see, these are the binomial coefficients. If we give specific values to the arguments of the cosine and sine, then these guys will collapse somehow, interestingly, and then boom, we will derive the sum of binomial coefficients in a certain way. But this is a different tactical battle. We do not want to fight it now. We want to concentrate on the powers of both cosine and sine in the expansion shown on the top. You know where it came from. You know what the last term is. So here we pay careful attention, because for the reasons that we all explained before and that now snowball into tactical and actionable mathematics, the trigonometric function of sine in this expansion will always be in the powers of what? The powers, the parity of these powers will be odd. 1, 3, 5, 7, 9, 11, 13, and so on. Odd powers. And what does that mean? That means that one copy of sine can always be factored from each and every term. One copy of sine, one copy of sine, one copy of sine, one copy of sine. When we steal one copy, one number, or one unit from a number that is odd, what do we produce? We produce a number that is even. That is why if we factor one copy of s from the expansion shown on top, so what do we have? S is raised to which power? Even power, 0. S is raised to what? Even power, 2. Even power, 4. Even power, 6, and so on, with the last term being what it is. We already know what it is. But now we know that our trigonometric functions, or symbols, if you will, lowercase c, lowercase s, are locked into the following relationship. This is circular relationship, if you will, c squared plus s squared equals 1. In one of the previous episodes, I explained how the hyperbolic functions can be constructed by direct analogy with their circular cousins. So this is our circular business. So c squared plus s squared is equal to 1. That means that in this case, what do we have for the square of c? We have 1 minus s squared. And then if c is raised to any even power 2q, then we have this expression that contains nothing but the second power of the trigonometric function of sine. And this exponent over here is an integer, positive integer. And why do we need that? Well, look at this. Our end goal is to sculpt a polynomial, an advantageous polynomial, whose roots can be used in the fundamental theorem of algebra, if you will. Such a polynomial can be expanded into a product, or represented as a product of the terms that are linear in the roots of such a polynomial. So how do we construct this polynomial? Well, in the polynomial, all the powers must be integral and they must be positive. So how do we ensure that even though in the parentheses over here, again, square parentheses mean no special value, just to provide enough visual difference between the binomial coefficients and the material that aggregates the whole thing. So here we have s. Look at this. Even power, even power, even power, even power. Very good. But now we have c over here. We want to produce c that is in the even powers as well. But how can we do it? Well, over here, look at this. Once we factor one copy of s out, we still do not touch the trigonometric function of cosine. Its powers are still the same. M minus 1, M minus 3, M minus 5, M minus 7, and so on. So how do we ensure that this material always produces a number that is even? Well, this is the requirement right here. If we demand by our will that the number M over here in the, just you saw it a few seconds ago in Demoivre's formula, if number M is odd, or representable as 2 times n plus 1 for a suitable integer n, then what will happen? Well, write it down. M minus 1, 2n plus 1 minus 1, 2n. Bam, we have our even number. M minus 3 will be what? 2n plus 1 minus 3 to n minus 2, factor 2 out, 2 times n minus 1. Bam, we have our even number. M minus 5, 2n minus 4, factor 2 out again, 2n minus 2. For n minus 7, it will be 2 times n minus 3, and on and on. So for all the finite number of terms, we now manufactured a power of the trigonometric function of cosine that is necessarily even. And what does that mean? Well, once we write it down over here, we see that all the even powers of the trigonometric function of cosine, 2n 2 times n minus 1, 2 times n minus 2, and so on, can be replaced through the fundamental, if you will, circular function identity as follows: 1 minus s, the trigonometric function of sine, raised to the second power, and the whole caboodle raised to whatever corresponding power of the cosine is. And once we do that, we replace this expression with this expression, then we will have the following result. Our sine of the integral multiple of the argument theta measured in radians can be represented as a product already. We're already manufacturing the product that we're after to begin with. You can see that this is already in the works. Sine, the trigonometric function of sine of the single argument theta, multiplied by the following expression: 1 minus s squared raised to the power n, over here n. Here we have 1 minus s squared raised to the power n minus 1, times s squared again. Remember, it's a show of s squared now, times some binomial coefficient, 1 minus s squared raised to the power n minus 2, but here s to the fourth power, so on, s to the sixth power, and so on for all finite number of terms. And what does that mean? Well, that means that, again, in some sense, forget about right now the exact shape of these factors, the binomial coefficients. We're not after them, even though, again, coming back to my previous argument of making this reasoning or this deduction templatizable, you can use it in order to manufacture your binomial sums with this particular funky looking coefficients. But now for us that doesn't really matter. What we're after is the fact that the material that we have in this expansion of the trigonometric function of sine is what already. Look at this. Nothing but s, nothing but s, nothing but s. So all we have is s. What's the minimal power of s? The sine. 2 is the square. And what are the rest powers look like? Well, the rest of the powers are positive. Look at this, positive integral numbers. They are positive whole numbers. n minus 1, n minus 2, and so on. So that means that the material that is present in this expansion of the trigonometric function of sine is a polynomial. Is a polynomial in what? Is a polynomial in this square right here. Which is to say that if as a syntactic sugar we'll designate s squared as u, a new variable, then we can rewrite this here expression over here, this expansion of the trigonometric function of sine, as follows. It will be s, still we keep the first power of s as is, binomial coefficient, 1 minus u raised to the power of n, another binomial coefficient, 1 minus u raised to the power n minus 1 times u, this is important, another coefficient, n minus 2 times u squared. Remember, over here it was s raised to the fourth power, but this is precisely the beauty of this manipulation. Show of even integers, one copy out. Show for the trigonometric function of sine, show of odd integers, one copy out. Even numbers, and even numbers are divisible by 2. So here all the powers of s are reduced by 2, and they become what? Well, it used to be s raised to the fourth, now it's u squared. Likewise, s used to be to the sixth power, now it's what? U cubed. And over here, 1 minus u raised to the power of n minus 3. But now what is important? Again, in other circumstances, it may be very interesting what these binomial coefficients are, and we can tactically manipulate them into submission in their own separate task. But here, look at this. What can we say about the powers of u? The powers of u are always not higher than n. N is the ceiling, the top. That's it. These powers can never come above it. Here, the u, again, whatever the expansion is, it may be quite horrible binomial expansion, but nobody cares. We look at the most senior term. It is u raised to the power n minus 1, but it collides with u raised to the first power, minus 1 plus 1, n. n minus 2 plus 2, n. n minus 3 plus 3, 3. So what we have over here on the top of the board is the material that contains nothing, no higher power of u than n. And that is precisely in all these powers, nothing is, no power is a radical, a square root, or a cube root. Nothing goes in the denominator. Everything stays above ground, so to speak. So we have a classical polynomial in the single variable u, single variable, single symbol polynomial of power n. The power of n is This is it. And don't forget that m, in our case, we demanded that m is a power, m is a number that is odd and representable as 2n plus 1 for a suitable integer n. So now if we go back and unravel all our temporary syntactic sugar substitutions, then we will have the following expressions, so that the trigonometric function of sine evaluated at the argument that is an odd multiple of some angle, 2n plus 1, some angle theta measured in radians, is again our sine of the single copy of the angle theta times the polynomial of power n in u, or if we spell it out completely, it will be the polynomial in this animal right here, sine squared. So again, you start seeing already how the product that we're driving to is emerging. So here we write down officially, what do we do here? Well, here we invoke the fundamental theorem of algebra. Such a polynomial is representable as a product of terms that are linear in the roots and in the variable itself of that polynomial. So it's a constant a times u, our variable, single variable that generates this polynomial, minus u1 times u minus u2 times and so on, u minus uk times and so on, u minus u sub n, and uk's are the roots of the polynomial pn. A is a constant. And now a very straightforward middle school arithmetic, if you will, takes over. What do we do with this representation of the polynomial? Again, you see, this is the idea of how we go down that rabbit hole. The fundamental strategic idea, as I explained at the beginning of this episode, is the following: the roots of polynomials, because again, due to this wonderful device called fundamental theorem of algebra, this is not always possible over the field of real numbers, but over the field of complex numbers, this is always possible. This expansion over here, terms are linear, and we will see in a second, once we get down to the manufacturing of the roots of this polynomial, we'll see that they're all distinct. They all have multiplicity of 1, and they're all nicely increasing, and this is the case. So now what we do over here is the following: from each term, u minus uk, we factor out minus uk. So if first we factor out uk, where u sub k is a particular kth root of this polynomial, we'll have u divided by u sub k minus 1, but we factor out negative 1. So once we do that, we'll flip these terms around, so it will be some constant a, we define it over there, times 1 minus u over u1 times 1 minus u over u2, and so on, 1 minus u over uk, and so on to the last term, 1 minus u over un. What is a? Well, this is very straightforward. Remember, we took out n copies of minus u sub k. So this is what we have: minus 1 raised to the nth power, and then u1, u2, and so on, un. The product of these roots, the product of the roots over here is straightforward. It's straightforward to understand. This is our new constant a. We will recover that value in a second, but now what I'm driving at is that we can, in order to recover the roots of this polynomial and the constant a, we can rewrite it over here. Look at this. It may be a little bit confusing, but I have only that much room, and I wanted to keep this expression for the expansion of the trigonometric function of sine as a skeleton, if you will, on which we hang more and more material, and that's how we develop the result. So once you write down the result like this, look at this. This is our expansion. 2n plus 1 for the odd multiple of the argument theta times sine of theta times a times and so on. We now can manufacture both the roots of this here polynomial and the value of the constant a. Wonderful. So how do we recover the roots of our polynomial shown over here at the bottom of the screen? Well, the argument is very straightforward. Look, we have a formation which looks like a number on the left-hand side plus a product of two numbers, the sine of theta times our polynomial. So if we can manufacture the following situation: 0 on the left-hand side and non-zero is the first product on the right-hand side, then what situation we will have? We will have, look at this, 0 on the one side equal to non-zero times blah. What is the choice for blah? For blah, there is only one choice. This blah should be 0, and that means the polynomial will be turned into 0 by what? By the numbers, which presumably participate in the formation of 0 here on the left hand side of this equal sign. And what will these numbers be? Well, these numbers will be precisely what we call the roots of this polynomial, because they turn that polynomial into the identical 0. So now the question is quite straightforward here. Again, in different tactical situations, you will work with different material. You will make these numbers odd, you will make them even, you will try to demand that this sign over here will be +1, -1, maybe it should be some other number, square root of 3/2, or whatever the case may be, and then you will manufacture your numbers here for the argument. Correspondingly, here we demand that the sine as a trigonometric function is 0 if and only if the argument is an integral multiple of pi, k pi, where k varies as 0, ±1, ±2, ±3, and so on. So this is it. If this material, let's look over here, look at the top of the board. If we look over here, this material must be equal to an integral multiple of pi. This here, right here, must be k, this guy, equals to k times pi. So what is theta? Theta will be k pi over 2n plus 1. But here we need to be careful. Look at this. So we already see that the numbers theta 1, such as pi over 2n plus 1, or 2 pi over 2n plus 1, and so on, or k pi over 2n plus 1, all the way to n pi over 2n plus 1, will be guaranteed to generate the zeros here on the left-hand side of the equal sign, or they will turn this sign into 0. But remember, we want to have two cases when this sign is 0, but this is important, I even underscored it with red, the sign of the single copy of theta is not 0. Remember, this guy cannot be 0. This is 0, but this cannot be 0, because if this is not 0, then there's only choice for the polynomial is to become identical 0, and that means we manufacture the roots of that polynomial. So here, the arguments shown over here on top, theta k, k pi over 2n plus 1, flip this guy, this sign, into 0. But now let's reason this. 2n plus 1 is greater than 2n for all, let's say, non-negative whole numbers. Even when n is 0, we have 1 is greater than 0. After that, on and on, this is all good. So the reciprocal values of this, the relationship is 1 over 2n plus 1 is less than 1 over 2n. Multiply both sides of this inequality by a one and the same positive real number pi, the inequality still stands. Multiply both sides again by k, k varies from 1 to n. We have this relation, and we suggestively replace it over here with pi over 2 times k over n. K in this case will vary from 1 to n, and that means what? That means that our angles, or the arguments theta k, vary between 0 and pi over 2. These guys that flip the sign of this argument, they manufacture a 0. But now we go back to our reasoning in terms of polynomial. We say that the signs that are squared of this argument over here, these numbers, the square of the trigonometric function of sine evaluated at this argument, they will be the roots u1, u2, uk, and so on, un. See, sine square, sine square, sine square. They will be the roots of our polynomial that we saw a few seconds ago. But the deal here is the following. The trigonometric function of sine squared, it lives in the upper half plane, of course, and is bounded from above by 1. But the important thing is that on the interval of interest from 0 to 2 pi over 2, this function is doing what? How does it change? How does it vary? That function monotonically is increasing. So with the increase in the argument theta, the value of the function increases. So first of all, what do we see? Well, all of our angles are distinct. They are distinct, and they are monotonically increasing, because this number right here, this can be taken to be a constant for a fixed n, and then the only thing that varies is k, but k varies monotonically, 1, 2, 3, 4, 5, and so on till n. So the angles vary monotonically. And then to these numbers over here, maybe I should have written these numbers with, these are the angles, theta 1, theta 2, theta k, theta n, and then this is how our roots are positioned over here, distinct and monotonically increasing with k. And then these guys right here, these are corresponding roots of our polynomial here. I should have written this here. Yes, this is how we do it. So this will be root 1, root 2, so on, root k, and then the last root n. You see, this is how these things work out. So this proves that our roots are distinct and are monotonically increase in value themselves. So all the terms that we saw in our polynomial are distinct and have multiplicity of 1. So they show up only in the product expansion of the polynomial only once. So now hopefully this is all clear. If you have any questions, the comment section is open. Ask away. But what do we do now? Now we simply take and determine the value of the constant a. And here is a short quiz for you to make this programming be interesting. If you were doing this problem, solving this problem this way, what would be your next step? The next step is, like I said, to determine the value of the constant a, but how would you do it? Well, the most natural thing to do is to flip u into 0, because look at this. If u is 0, we have 0 divided by non-zero number is 0, 1, 1, 1. So the whole thing collapses into unity. But if sine square of any of our angles is 0, that means that the angle itself tends to 0. And here it is important to understand that we fulfilled our promise initially that the angles theta k that deliver this requirement and this requirement would deliver on the promise of this requirement. We have it such that the sign of this argument is 0, but at the same time, the sign of the single argument is never 0, because the sign of this here angle is never 0. But once we determine the value of the coefficient a, we have the right to set this value to 0, and that means that the underlying value of angle theta will be 0. Again, we cannot do the straight division. We have to take the limit. As such, the value of the constant a is given by the limit of this ratio of sine of odd multiple of the angle theta by the sine of the single copy. Why is that? Well, look at this. 1, 1, 1. So a is equal to this sine divided by this sine, and we take the limit. So once we take the limit, and we will be taking quite a bit of limits like this in the upcoming segment, so you should be at home with manipulating these limits. And in this case, it's actually quite straightforward. All we have to do is recall our favorite limit, which I do not prove. I'll treat it in the utilitarian sense that the limit of sine of x to x when x tends to 0 is 1. This is the one. Back in my time, it was called the first remarkable limit. The second remarkable limit was connected with the Euler's constant, the base of the natural logarithm. So once we know this result, we simply sculpt all sorts of incarnations of this result in the given one. So what do we do here? Well, we divide by 2n plus 1 times theta, divide, and then we multiply by 2n plus 1 to compensate. And if theta was in the numerator, we can put it into the denominator of the denominator, and voila, we have our one remarkable limit, the other remarkable limit. The limit of the product is the product of the limits, provided that the limits exist. The fundamental basic theorem in real analysis. The limits exist over here. 1, 1, what is left? 2n plus 1, or m, which is our a. So now we go back to our original shape of the polynomial, and finally we rewrite it this way. The sine of 2n plus 1 times theta, this is our guy right here, divided by the value of the constant a, which we just determined, 2n plus 1 times sine theta. This is this guy. We simply took this material and move it to the denominator of the left-hand side. There is nothing to it. It's just a little bit more compact and more tactically advantageous. We will see, and we'll understand why in a second. And then we have our product of n terms, where the k, the multiplication variable, k varies from 1 to n, and the structure of the common factor over here is this: 1 minus sine square of theta divided by sine square of k pi over 2n plus 1. Now, don't forget, and in some sense, okay, we can leave it at that. Just taking this identity alone already is a good result. Remember, in my time, all the verbal exams were in mathematics, physics, theoretical physics, and computational sciences in the verbal face-to-face real-time interrogation format. So if you can get that far on the corresponding, let's say, real analysis exam, you're already doing well. And this formula right here presents its own interest. It can be spun tactically into all sorts of interesting material and results, but we drop it on the floor cold turkey over here. We do not need it right now. We'll move on. And the way we will move on is as follows. We'll rescale this variable right here, the angle theta. And the rescaling is done as follows. X is equal to 2n plus 1 times theta from here. Theta is equal to x divided by 2n plus 1. So here the argument becomes x. Sine of x divided by 2n plus 1 times sine x divided by 2n plus 1. Look at this, because theta over here is what? X divided by 2n plus 1. Theta, pay attention. And the remaining squares of the trigonometric function of sine are dealt with accordingly. X divided by 2n plus 1, and here nothing changes. This thing remains the same. So this is the intermediate result. This is the intermediate result that we will manipulate, as follows. Observe that one and the same number, 2n plus 1, 2n plus 1, 2n plus 1, and 2n plus 1, is present in our formula in a uniform fashion. It shows up in the same shape all over the place, so we can go back and collapse it into what we had it before. M, 2n plus 1 is equal to m. Why? Again, this is syntactic sugar, so we do not have to write 2n plus 1 all the time. We could, and to younger students of mathematics probably that will make sense, but with time, as you grow up, you will learn to deal with these things. It may seem a little inconsistent over here that we have the product variable k, but there is k over here, and n shows up, but there is no n over here. Well, n, remember, implicitly is over here, so we can say that n is equal to what? M minus 1 over 2. You see, this is the deal. So either way, when we tend n to infinity, m goes to infinity, and conversely, if m goes to infinity, positive infinity, n goes to positive infinity. So either one of these symbols that grows without bound causes the other symbol to grow without bound. N grows, m grows. M grows, n grows. Either way. And the idea here is the following. Now that we have this result, don't forget that this is the material that we want. And for tactical manipulations that we're about to engage to, again, dragging this 2n plus 1 all over the place does not make any fundamental difference. And in some sense, again, with time, you will learn that the more compact things are, the easier they are to deal with. And 2n plus 1 is less compact, m is just compact. So here we have it. Sine of x over m times sine x over m. And here we have the product. This time, don't forget that the number, the polynomial, by its definition, is a structure that has a finite number of terms. The power of that polynomial is finite. The number of roots is finite. Everything is finite, so the number of these factors over here is finite. But the idea now is to take this here result and carefully take it apart with a rigorous enough treatment into the final product. You will see how this unfolds into the product that we're after. And here I had to say that in the past, Leonhard Euler produced that result, but we now know that Euler was skirting fallacy, or he was flirting with fallacy, if you will. But in some sense, maybe that is one of possible reasonable definitions or explanations of a person who is enormously talented. Of course, Euler was enormously talented person, is that such an enormously talented person and enormously technically capable person can flirt with fallacy. That person can gently touch incorrectness, but still in the long run and nonetheless stay on the correct side of mathematics. And as I mentioned before, Euler was a man of an immense technical talent. Even though he was skirting or flirting with fallacy, in the end he came out to be on the right side of mathematics, and we now know that the expansion that we're shooting for is of course correct, but Euler used a slightly different idea to derive it. So here the other aspect of this exercise is to show what is the real cost of mathematical rigor, and here the situation is the following. The younger students of mathematics unfortunately do not really understand what rigor is and how to use it. It will take years and years of practice for them to develop that skill. And on the other hand, when they are showed even a little bit of rigor, then invariably they start complaining, why is it so difficult, why is it so complicated? And the truth of the matter is that it's not complicated, it's not difficult. Mathematics is what it is. Mathematics is under no obligation to dole out special intellectual flavors to us. In the frame of reference of mathematics, things are what they are, and it's only our feeble minds are to blame if we cannot comprehend the structure of what is going on with mathematics. In other words, the fault lies squarely with us. So here, let us just take a glimpse of what a rigorous argument should be. So now we need to show that since we are developing an infinite product, by definition, the product is said to be convergent if the limit of its partial products exists, number one, and it is distinct from zero and either infinity. In other words, the limit of a partial product is let's say, real number that is not zero, that is not positive infinity, that is not negative infinity. So we need to work with limits carefully. Overall, our goal is to drive this whole situation to the point where we have m, the number m, which is connected with n, to grow without bound, and we want to see how the terms in our product eventually behave once this growth without bound takes place. And the way we do it is as follows. First, we fix any non-zero value of x such that its absolute value times 2 over pi obeys this constraint. Any two whole positive numbers, p and n. And again, don't forget that some would use n and m interchangeably. It may be confusing to some, but once you get used to it, it is not that difficult. So here we rewrite our product as another product of two objects. One object is the product that you see over here on the right side times the residual product r with the index, subindex p, which is also a function of x. So here we vary the dummy multiplication variable k over here from 1 to number p, shown over here. And then in the residual product, we vary the summation, the multiplication index k here from p plus 1. This is important to understand, p plus 1 to n. And we now want to get a bound on the residual product to see how this residual product will behave once we tend m to infinity, and at some point here we will take p to infinity on its own separately. So in order to do that, we agree that we see that for all the indexes k in this residual product, that means here and here, especially here, especially over here, x is less than k times pi over 2. This is how we fix our value of x. Also in the previous segments, we showed that k times pi over 2n plus 1, because remember m is 2n plus 1, is less than pi over 2, and that means that if we divide both sides, this by 2 and this by 2, the inequality stays. So k pi over 2m is less than pi over 4. So now next step is to bring in it's kind of mysterious where did the cosine of square come in, but once you see the manipulations shown over here, you will understand where it comes from. So in a way, I put the cart in front of the horse a little bit, but it's easier that way. So the cosine squared on the interval of interest between minus pi and pi over 2 will be behaving which way? Well, it's a square, so on the negative part of this interval, it is monotonically increasing. On the positive part of this interval, it is monotonically decreasing. But because this is a square again, it is interesting what's happening over here in this side, only on the positive side. So if we apply the cosine square to both of these numbers, which are locked into this relationship less than, if we apply the cosine square, then the sine here will be the opposite. Why is that? Because to the smaller values of cosine here, to the smaller value, you see, there corresponds a larger number. So if the argument is larger, then the value is smaller. So this is where the greater than comes in. So cosine squared of pi over 4 is trivial to compute. Square root of 2 over 2 squared, 2 over 4, 1/2. So this is what we have with our result. Now we want to see how this thing behaves. We want to get, in some sense, an upper bound on this ratio. And then once we start multiplying this factors together, want to get the handle on the product of these factors once we stick them one to the end of the other. So here we have the squares obviously must be greater than 0. These are the real numbers. And again, recall that the sine square on the interval of interest is monotonically, what's it doing? Decreasing. So not decreasing, is monotonically, what did we see? We said increasing, I'm sorry, it is monotonically increasing. So we have, for the ratio of these two terms shown over here in the residual, we keep the denominator the same, but we replace the numerator x over m with k pi over 2m. See, this guy right here, k pi over 2m. And x over m is less than, this is how we picked x, is less than k pi over 2m. And for the larger arguments for the sine square, they correspond larger values, because remember, it is monotonically increasing. Again, all these statements, they in some sense must be also proved by themselves. So here we in a way see the true cost of rigor, because all these claims that I'm making right now on the fly, that the sine square is monotonically increasing, proof must be generated. Cosine square monotonically decreasing over here, proof must be generated. All these statements must be proved, and this is how the total cost of rigor is acquired. So here we take the sine square of angle and use the double angle identity. We represent this as twice some angle. Which angle? Twice 1/2 of this. 2 becomes 4, and then we have 4 times sine square of k pi over 2m, and this sine square with this sine square will cancel out, and what will remain? What will remain is the 4 cosine square of k pi over 2m, precisely our usual suspect over here, and this is why this manipulation started. So in a way, I am playing it sort of backwards, but once you think about the way to construct that proof, you will play with the ideas in some nonlinear way. Try this, try that, try this, try that. Then you will say, oh, okay, this is the bound, but how do we get here? Well, this is how we get here through all these arguments, and once you string them together and deliver in forward flow of causality, it becomes difficult and complicated. But in a sense, it is not. So now we see that once the cosine square, we got the bound on this guy right here, must be greater than 1/2. Its reciprocal must be what? Less than 2. So this whole thing is less than 2 over 4, or 1/2. So now remember this 1/2. We see that we have this bound on this term is 1/2. But what is the structure of our factors in the residual product? It's 1 minus. So roughly speaking, it's 1 minus some material, this guy. We want to make it less than 1 minus something less than 1/2. So we want to somehow figure out what is going on. How can we get a good solid bound on this thing? See this? It looks completely childish and not really actionable, but in reality it is. And the key to the actionability of this situation is the following. We want to decompose our favorite function e raised to the power minus 2 some magnitude beta, but beta over here will be specifically less than 1/2. This is the thing with mathematics. Whenever you look at a particular manipulation with the microscope, it makes no sense whatsoever. It's very bewildering and not clear what is going on. And the only way to gain any clarity, any intellectual grasp, to get a grasp on what is going on, is to have a strategic view. And strategic view over here one more time. I want to make sure that everyone on the audience is on the same page. We want to handle our product not in a loose fashion like Euler and mathematicians of his time 200 years ago, but we want to handle it in a rigorous way and construct a watertight argument. And the way we do it is we sneak up on the limit that's lurking over here in 2 steps. First, we keep the value of x and p fixed, but then we tend m to positive infinity. We make m grow without bound. And then after we handle that limit, we now tend p to positive infinity, let it grow without bound, and then we get our nice rigorous product. So here to that end, we already remember that we got the bound in the previous segment. We got a bound on this animal right here. We showed that for all possible values of k, for all the arguments of sine here in the numerator and denominator, it's strictly less than 1/2. And that 1/2 motivated the following idea. We have 1 minus something. You see, on the one hand looks innocent, but on the other hand, we do this maneuver in physics all the time. We bring in a useful expansion. And what expansion? Well, the power series. Remember, when t is, whether it is real or complex, we have our power series expansion for the exponent right here. So according to this expansion, now we do this. This motivates the choice of the real number beta. This is basically will be stand-in for this guy. This is how we will gain, or in some sense less so, have a control on the variance of these guys in a way that we can handle and come up with explicit analytic expressions. So beta is greater than 0 and less than 1/2. Multiply this by 2. 2 beta is less than 1 and greater than 2. Multiply this again by beta. And remember, beta is positive, so signs stay. So 0 less than twice beta squared and less than beta. And why do we need it? Well, look at this. We now manufacture, according to our need over here, 1 minus something. We want to manufacture this 1 minus something, and we do it with the exponential function. So once we decompose this particular exponential function according to the power series expansion, we have 1 minus 2 times beta plus square of the argument divided by 2 factorial is 2. 2 and 2 cancel out. So what do we have? More terms over here. So if we just grab these two terms, when we subtract something from this whole expansion will be less than just this finite number of terms right here, than just these 3 guys, 1, 2, 3. And once we show that 2 times beta squared is less than beta, then we can say that these 3 terms are less than 1 minus 2 beta plus beta. Remember this relation. So 1 copy of beta subtracted from 2 copies of beta is 1 minus beta. So here that means that our expansion here is given by this. And why is this less than 1? Well, because remember, from 1 we're subtracting beta. That's the number that's less than 1/2 and more than 0. And again, in some sense, I probably should have dwelled more time explaining why this inequality holds over here, why grabbing just the first 3 terms over here makes these 3 terms larger than the rest. But to keep the size of this episode manageable, we will move on. So here we will have this relation over here. And now once we associate beta with this term over here, this is how we construct it. Remember, e raised to the power minus 2 times that thing, so exponent raised to the power minus 2 times, this should be transparent from here to here, jump back and forth, this is what's going on, times this is less than 1 minus beta, 1 minus beta, but this is our beta right here, this is beta, you see, 1 minus beta, and we show that it's less than 1, less than 1. So now what do? Well, we have one copy for k, but now we start multiplying, because we showed that these estimates are true for all k. We start multiplying these factors one with another. How many times? Well, the needed number of times. The needed number of times from p plus 1 to n, whatever that number is. And once we do the exponents, the multiplication of exponents translates into what? Into the sum of this power. So on the left hand side we will have exponent of what? Minus 2 times sine square x over m. There is no k over here, we can factor it out, but here we have this beautiful sum that runs from p over k over this dummy summation variable k, from p plus 1 to n, 1 over sine square of k pi over m, and this will be on the left side of this chain of multiplications. But in the middle, what we will produce? In the middle, we will produce exactly our residual product over here. And since we showed that this inequality holds over here, so with all the products piled on top and bound by less than 1, times 1, times 1, times 1, and on, the less than 1 will hold. But in the middle, over here, this whole thing multiplied together with each other the appropriate number of times will give us the residual product, Rp of x. You see, this is how we develop the way to control the magnitude of this residual product, and this will help us in the next step. But what do we need to do now? Now we need to deal with this exponent over here and get a handle on this sum. This sum looks pretty wild, but it turns out that we can deal even with that. And the way we get a handle and the control and the bound on this trigonometric sum over here, the sum is finite, remember, runs over the summation variable k from p plus 1 to n, is as follows. We already showed that all our arguments belong to the subset of real numbers from 0 to pi over 2, and here that is why we bring in the so-called Jordan's inequality. This inequality can be shown with elementary means completely. It's within the grasp of any sufficiently motivated high school students. Taking the first derivative of this function over here, looking at what happens over there, this result holds true. This part right here, this is the inequality, and now we set in this inequality for the angle alpha, we set it equal to k times pi over m. So once we take this inequality, the Jordan's inequality, and flip it upside down, take the reciprocal, then its left and right sides trade places. So in the linear power, we have 1 over sine greater than 1 less than pi times m over 2 times k times pi. Where did this come from? Well, we simply took alpha and moved it downstairs. So pi over 2 alpha, pi over 2. And what's alpha? Alpha is k times pi divided by m. M goes here. That's it. It's that straightforward. You can see already pi's cancel out over here, but let's keep it that way. So multiply this inequality by itself. Produce a square of this guy. So what do we have here? Well, again, here at this point, pi square and pi square, let's say, cancel out. And what do we have? M squared in the numerator, 4 times k squared in the denominator. What kind of bound can we produce for this guy? Well, look at this. K is larger than k times k minus 1. And once we take the reciprocal, the quality of the sign changes. 1 over k squared becomes less than k times k minus 1. And then what do? Partial fractions decomposition. That's right. 1 over k times k minus 1 comes out to this guy. 1 over k minus 1 minus 1 over k. But here is the good news. We have over here a finite sum, a finite number of terms. But if we tend the number of terms in the sum that runs over this index k to infinity, we're definitely grabbing, in some sense, all the possible terms. We take way more than we actually need. So this sum over here from p plus 1 to infinity is what is a telescopic. If you missed this episode on this channel, we studied the telescopic series in great detail in the episode called One Telescope, Two Telescopes. I explain all the details that you wanted to know, or maybe you did not want to know about telescopic series. This series is evidently telescopic. So once we start iterating k plus 1 plus 1 plus 1, then the terms will cancel out. So bottom line, the only term over here that will survive in the long run once we take the limit is 1 over p. Isn't that wonderful? That is absolutely wonderful, because now we have an upper bound for our sum that runs from p plus 1 to n, this wild animal right here. As a matter of fact, on this channel, we actually evaluated this finite sum, but I do not recall. I think the range of k was complete from 0 to something. Anyway, we have an upper bound for this here sum. So this finite sum is less than 1 over pi. And now there is a string of symbols over here, but I suggest we read it from right to left, not from left to right, because otherwise it gets a little confusing. So before we show this inequality right here, look at this, concentrate on this, whatever you see on the right side of the board. So we remember, how did we produce it? Well, we multiplied a bunch of inequalities that we established together, expansion of the exponential function, yada yada, and we have it less than our residual product, and the residual product itself will be less than 1. Now, once we got the handle of this, look at this. This sum is less than this particular value, but this exponent is what? Is negative. So what does the graph of negative exponent look like? The graph of negative exponent looks like this. It goes like this. So to larger value of the argument corresponding, smaller value of the function. And conversely, to the smaller values of the argument correspond larger values of the function. This is smaller, then the value of the whole thing is larger. So this exponent is larger than our infinite sum right here. You see, than our infinite sum right here. And we already evaluated here. There's an equality sign, because precisely this sum is equal to 1 over p. And this is what we have, m squared over 2 times p over times sine square x over m. The negative sign over here we brought from the expansion. We know where did it come from. Where did 2 creep in over here? How did 2 percolate into this thing? We have 2 in the numerator, but here 2 in the denominator. Well, don't forget this 4 right here, this guy 4. Remember, 2 over 4 becomes 1/2. So from here, when we jumped over this sign, we have 4. We have 2 in the denominator, but we have 4 in the 2 in the numerator, but 4 in the denominator. 2 over 4 becomes 1/2. So half, this is it. So now this result over here, connect this in your mind's eye, connect this, chalk this result up. We'll come back to it in a second. This result with this result. This is what we're driving at. See, like this. So our exponent shown over here is less than the residual product, and the residual product is less than 1, and you already should feel what is going on. So here we have, look at this, 2 variables, m and p. Now with fixed x and p, we will tend m to infinity in the next step. When m tends to infinity, what happens to the argument of the sign? It tends to 0. So now we will be computing another beautiful limit, m squared times this sine squared, when m tends to positive infinity. And to that end, keeping the variables x and p fixed, we pass to the limit when m tends to positive infinity in our main workhorse relation shown on the upper right side of your screen, where m is in the denominator of the ratio and in the denominator of the argument of the trigonometric function of sine, and on the left hand side and on the right hand side and somewhere over here. Now we compute the left hand side limit as follows. Taking the limit of this ratio when m tends to infinity, we manufacture our favorite remarkable limit, sine of x divided by x. When x tends to 0, this becomes the positive unity. And over here we manufacture the following limit. Here we divide this ratio by x, shown over here, and then we multiply it by x, so that these two x's cancel out, but we move the x from the numerator of the total ratio into the numerator of the ratio that plays the role of the denominator of the denominator. And we take the integer m and move it over here, so that way this integer m actually sits over here. So even in this format, x and x cancel each other out. That is the same thing. But here we use the basic theorem from real analysis. The limit of a product is the product of the limits, provided that the limits exist. In this case, the limits do. This portion over here shown on the left side does not depend on m, so it percolates into the answer. But here we have the limit of 1 divided by something. Again, the fundamental theorem from real analysis. The limit of the ratio is the ratio of the limits, provided that the limits exist. The limit of 1 is 1, and the limit of this formation, when m tends to positive infinity, the whole ratio tends to 0, this is 1. Boom, we have our result for the limit on the left hand side, the trigonometric function sine of x divided by x. And now remember that we keep the variable p fixed at certain value. It does not change. X is fixed, so the only thing that varies over here is m. And this product is finite, a finite number of factors. So again, we apply the same theorem. The limit of a product is the product of the limits, provided that the limits exist, and on and on and on. So we shrink these limits together. So once we move the limits through, we come down to this limit over here, and we manufacture this limit pretty much the same in the same way that we did this one. We divide the numerator of this ratio over here by x squared by m squared, y x squared by m squared. Well, sine is raised to the second power, and the argument x divided by m. So x divided by m squared, m tends to infinity. This little ratio tends to 0 correspondingly. So we have our limit, and once we divide it by this ratio, we need to multiply in order to compensate. This is one side, and then we have to deal with the sine square of this argument, k pi over m. Here we do the same thing, k pi over m. We divide this sine by this ratio, k squared pi squared over m squared, and we multiply by it. You see, this k pi squared and this k pi squared cancel each other out, and then when this m squared is percolated over here, it cancels each other out. So what do we see now? We see that this is the limit that becomes 1. This is the limit that becomes 1. And what do we have here? We have m squared and m squared over here cancel each other out. And what survives in the end? In the end, we have the following material that survives: x squared in the numerator, x squared in the numerator, and k squared times pi squared in the denominator. And this is the answer. And now you already start seeing how our answer begins to emerge. And once we write down our results over here in the bottom, we have, as a result of taking the limit of this expression through, when m tends to positive infinity, x and p is fixed, we have this: sine of x divided by x is equal to the product over the dummy multiplication variable k that varies from 1 to p. Remember that p is, at this point, is fixed. We have this finite product of that many terms, p terms, x squared over k squared times pi squared, times the limit of our residual product, remember. And we will deal with this residual product, with the limit of this residual product, based on the bounds that we developed in the previous segments, as follows. Namely, going back to the bound that we established for our residual product, shown over here, we now take the limit of this expression through when m tends to positive infinity. Remember, x and p are still fixed. And the way we do that is we transition from strict inequality to inequality that contains the equal sign, because this is what can happen with limits when m tends to positive infinity all the way through. Here on the right hand side we have the positive unity 1. There is no material that depends on m. Here we keep it as it is. We will designate this limit as the letter L in a second. We understand what's going on, but here we need to compute the limit of the exponent that has this as its power, this expression as its power. Again, we use all sorts of wonderful theorems from real analysis, where we capitalize on the fact that the function that we're dealing with is continuous at every point. We'll move the limit through. All these words needs to be said, but as I mentioned before, when the younger students of mathematics are shown what the even approximately complete mathematical rigor looks like, they start crying foul. And now we see the true cost of rigor. So here we move the limit through the exponent into the argument, and with the argument over here we have this wonderful limit m squared over 2p, but this material we do not care. That doesn't really matter. What matters over here is m squared and the material in the argument of the trigonometric function of sine squared. So now we compute this limit over here. How do we do it? You already know the maneuver. We divide the sine by x squared and we multiply it, and then we move m squared from the numerator into the denominator of the denominator. So it becomes x squared by m squared. This limit over here is what? Well, when m tends to positive infinity, then the ratio tends to 0, argument tends to 0. We have our positive unity times x squared. Boom, we have our limit as x squared of the material that varies in the argument of the exponent. But what does that mean? That means that the limit of our exponent when m tends to positive infinity has the following expression: e raised to the power minus x squared over 2p. Remember, x is fixed and p is fixed in this first stage when we take the limit of this expression through when m grows without bound. And what does that mean? This fact, what does that mean? That means that our expression that I spelled out for you over here in the middle of the board can be collapsed if we call this object over here L. So we have the following bound on L. It's less than or equal to 1 or greater than or equal to e raised to the power minus x squared over 2p. And this limit, again, one more time, this is the bound on this limit right here. And now what can we do? Well, now that we have this material, we can apply the second stage of dealing with this infinite product, where we will keep x fixed, but we will tend p to positive infinity. And since in the previous segment we proved that our limit L exists, we can have two cases over here. When this limit is 0, then that means that the value of the trigonometric function of sine evaluated at the argument x is 0, and we have our relation that we're trying to prove trivially holding true. And if this limit is not 0, then we squeeze that limit between two real numbers, one on the one side and the other number on the other side. What's that number? Well, here we will need to compute the limit of this expression, but this time, remember, in our previous step we kept x and p fixed and we tended m to positive infinity. Now we tend p to positive infinity, but x is fixed, and we take the limit of all the material that we have so far through when p tends to positive infinity or grows without bounds. So here the limit of the exponent with this argument when p grows without bound is trivial to compute depending on how you want to slice it. It could be 1 over e raised to the positive power over here. P tends to positive infinity. Again, the limit of a continuous function, we can move it upstairs over here. The limit of 1 over p when p grows without bound is 0. So we have 1 over e raised to the power of 0. 1 over 1 is 1. Hallelujah. So in this case, if the limit L is not 0, then it must be 1. Remember, we trapped it between two numbers, so by the corresponding squeeze theorem, we know that this limit must be 1. And in this case, when we take the limit of the left-hand side of our relation, remember once we got rid of m, we have our left-hand side. When p tends to positive infinity, there is no material that depends on p. So that ratio comes out from the limit as it is, sine of x divided by x. And there we have it. Sine of x divided by x is the product of these terms over here. 1 minus x squared divided by k squared pi squared. K, the dummy product variable, varies from 1 to positive infinity. That relationship can be rewritten as shown over here in the original form that I presented at the beginning of this episode. Sine of x is represented as the product of the argument x and the infinite product shown over here. This is our result that holds true for all real x that are not integral multiples of pi. And this is right now, if I'm not wrong, we're coming up on about 90 minutes or hour and a half of me talking about the results that I pre-wrote on the board for you. Remember at the beginning of this episode, I said that in this episode, I will not be writing as the solution develops. I will pre-write this information and then discuss it. And even in that format, it took us about 90 minutes or hour and a half to arrive at the result. And over here, I'm pretty sure that more words need to be said about the existence of the limits that we discussed over here. Our limit L, we will have to refer to the previously proven theorems. These theorems usually connect infinite series with infinite products because there is a tight connection between the two. And depending on how your course is structured, certain theorems will be used, must be wedged in over here. The point is that this is what more or less grown-up mathematics, that is more or less rigorous, looks like at close range. This is what it takes to produce a result. Some of these results were known to Euler back 200 years ago. Some of them were not, but in modern times, this is one way to construct a rigorous argument that proves the decomposition of the trigonometric function of sine into the infinite product shown over here. And now we can look at the following three very straightforward applications of this formula. And before we start looking at the straightforward applications of the formula that we just developed, a piece of sobering news which comes down to the following. This episode alone already shows that most people cannot not only do mathematics, but most people cannot even handle mathematics, because on the one hand, doing mathematics requires the ability to operate at the intellectual level that is all in its own separate space, so to speak. And handling mathematics means that doing precisely what we're doing right now, put some number of people in the room, show them what more or less grown up mathematics that is more or less rigorous look like, and the people cannot deal even with that, because most people unfortunately do not have the intellectual stamina and the intellectual discipline to just handle mathematics. But anyway, so here, now that we proved our formula for the infinite product of the trigonometric function of sine, valid for all non-integral multiples of pi, we can squeeze some amount of useful information from it as follows. Trivially, when x is equal to pi over 2 is a rational multiple of pi, truly a rational multiple of pi. This is not an integral multiple of pi, sine of pi over 2. Then according to our formula over here, 1 is equal to what? Pi over 2. And then we have 1 over 4k squared. Why is that? Pi squared over 2 squared. Pi squared and pi squared cancel out, 2 squared 4. So this is what we have. We flip this ratio to the left-hand side as 2 over pi, 4k squared minus 1 over 4k squared. We split it as follows in the product of two positive integers. Here we have a square of the same integer, and that means what? If we take the reciprocal of this, and we will have pi over 2 is equal to reciprocal of this, 2k squared over the product 2k minus 1, 2k plus 1. We partition them suggestively suggestively as follows, and we obtain the so-called the Wallis product for pi. The convergence of this formula to pi is actually quite slow. I wrote a program to see for myself how fast the numbers converge to pi, and it takes about half a million of terms. And by term, we mean not one term, two terms, but the whole thing. These two products will count as one term, so about half a million, give or take, of terms to get to the 6 significant digits coincidence with pi, for what it's worth. And the material that you see over here is quite straightforward. We will need this formula. We will come to this formula in the near future when we will be evaluating a certain integral, as a matter of fact, in the next episode. But once we have this material over here, it can be massaged into all sorts of factorial notations, but this is a very straightforward way to wrap your brain around how pi can be represented as a product, look at this, of ratios of nothing but positive whole numbers. Next, we can conduct the same experiment with the trigonometric function of cosine. Remember, in the previous segments, I showed you two expansions of the trigonometric functions of cosine on the top, sine on the bottom. We can structure the polynomial for the cosine in a similar way and conduct pretty much the same experiment, or we can basically torture the polynomial, the roots of polynomial idea for the cosine. But many times the way these things work in mathematics is that once we do a lot of heavy lifting once, we try to dance around this heavy lifting in clever ways and avoid this heavy lifting and manipulate the material, similar but different material, into submission without going through, but going around, but obtaining the same result. So here we can do the following experiment. For example, we represent the trigonometric function of cosine through this obvious middle school identity: twice sine of x cosine of x divided by 2 sine of x. 2 sine of x cancel out, cosine remains, and then we take our decomposition of sine of the trigonometric function of sine into an infinite product and replace the argument of x with 2x in the numerator. We keep the same argument in the denominator. 2x and 2x cancel out. We have this ratio. This usually looks quite scary, but if we conduct the following experiment, then we will see it's not that scary. 1 is the same in the numerator as the same is in the denominator. Minus in the numerator, minus in the denominator. Same things in the numerator and in the denominator, so we realize that the structure of the term over here in the numerator is basically the same as the structure of the term in the denominator. The only difference is this multiple of 4 in front of x. So we can forget about x squared and pi squared, don't care, 1 minus, only concentrate on 4 over k squared in the numerator and 1 over k squared in the denominator. Compile the table that I showed for you by yourself, experiment away, write down more terms, and this is what you will see in the top row. We show the numbers 4 over k squared. This is 4 over k squared. Let's say I'll write it down like this: 4 over k squared, and this is 1 over k squared. You see, this is the top row is 4 divided by k squared, and the bottom row is 1 divided by k squared. We simply roll through this material, and without thinking too much about it, simply write down the ratios that we obtain as we vary k from 1 to 2 to 3 to 4 and so on. And this is the result that we obtain. We can actually predict this somewhat theoretically as follows. Look at this. When k over here and over here, when k is 2k, in other words, when the number k becomes even, then for this ratio over here, 4 over k squared, what do we have? 4 over 2q squared. 4 and 4 cancel out, and we have 1 over q squared. So what does this tell us? This tells us that at some point in the future, when q is large enough it in the denominator, in the numerator over here on top, because 4 cancels out, we will have the number that we stepped on before in the denominator over here, because remember, this k varies as 1, 2, 3, 4, 5, 6, 7, but the even numbers over here in the denominator of the numerator shows up every other time. So once we compile the table, we see the following interesting phenomenon. We see that, for example, when the number becomes a perfect square, here we have it in some sense too, because look at this, for k equal 2, we have 1 over 1 for the numerator and 1 over 1 in the denominator. So in this case, 2 is raised to the first power. We do one step backwards and one step down. So we have it, if you will, we can cancel these two fractions out. Now we have 2 raised to what? To the second power in the numerator, and we stepped on it how many terms before? Well, that many terms before. 1, 2, down. So we cancel 1/4 and cancel 1/4. Next, we have when 5 is the squared, it's co-prime with 4, nothing good happens. But when we have 6 over here, so what do we have? We have 4 in the numerator divided by 36, or 1 over 9. This is our, see right here, 1 over 9. And what is 9? 9 is 3 squared. So 3 was seen over here, 3. See, so we go 1, 2, 3, down. So this is how these things roll. When we step on another even number, 8, this is what? This is 2 raised to the 4th power. So how many steps will go back? 1, 2, 3, 4, down. So 1/16 and 1/16 go. So now 10. How many numbers do we step back? 5. 1, 2, 3, 4, 5, down. So there you go. You see, cancel out, cancel out. The point is that all the numbers that are sitting in the denominator over here for k eventually will be probed by the numbers in the numerator, and all these numbers will cancel out. All these numbers will cancel out. If you conduct this experiment further, all these numbers will cancel out, and these cancellations mean what? These cancellations will only take place when k is what? When k is even. When k is even. So which terms in this ratio of products will survive? Only the terms that correspond to k that is odd. 1, 3, 5, 7, 9, and so on. And there you have it. This is the decomposition of cosine. Product over the dummy variable k that varies from 1 to positive infinity. And the structure of the common factor in this product is what? 1 minus 4. This time it's 4x squared. 4x squared divided by not the square of k as it was in the sine, but the square of an odd number, 2k minus 1 squared, times pi squared. And for the road, one more low-hanging fruit that we can pick almost instantly from this expansion of the trigonometric function of sine into the corresponding infinite product. And this low-hanging fruit is called the reflection formula for the gamma function over here, but this time it holds for all x that are not integral values. In other words, x is not equal to 0, plus minus 1, plus minus 2, plus minus 3. The way we deduce this instantly is as follows. We scale x into pi times x. And over here, we basically uniformly replace x with pi times x. Pi times x, pi times x, pi squared with pi squared cancel out. And in this case, we have the following relationship. Sine of pi times x is equal to pi times x times our infinite product over k, where we have the following structure of the common factor. 1 minus x squared divided by k squared. This time, pi vanishes from the denominator. No more pi. Now we go back to the definition of the gamma function with which Leonhard Euler, the Swiss-born mathematician, worked, and this is how he introduced. It's not the long story of where did this definition come from. Unfortunately, most modern students have no idea about this definition. They're used to the integral representation of the gamma function, but in some sense. Maybe this way or that way, this is how the gamma function has begun its life. So here we have 1 over x times the infinite product of the following ratio. 1 plus 1 over k raised to the power of x in the numerator, 1 plus x over k in the denominator. Using this definition, it can be deduced, it can be shown that gamma of 1 plus x is equal to x times gamma of x. Now here we turn around and we flip this guy by changing x to minus x. We take the positive opposite sign of x, and then we put negative x into this formula uniformly again. So 1 plus x becomes 1 minus x is equal to minus x times gamma of minus x. And now we go back to our definition. And what do we do with gamma of minus x? Here we replace x with minus x uniformly. Minus 1 over x minus x minus x over k. Minus 1 over x times minus x cancel out, so we have the product. In the numerator, we have the same numerator, but then this time it's raised to the power minus x. And in the denominator, we have 1 minus x over k. You see, this is what it is. And now what do? Well, we simply glue this definition of gamma of 1 minus x to the original one, gamma of x. Once we construct this product, gamma of x times gamma of 1 minus x, we have 1 over x. This comes from the gamma of x, and then the product of what? Look at this, 1 plus 1 over k raised to the power of x for the gamma of x, and the same term raised to the negative power of x. When these two terms collide, plus x and minus x annihilate each other. We have positive unity in the numerator, and in the denominator, what do we have? 1 plus blah times 1 minus blah. This is our favorite middle school a plus b times a minus b, a squared minus b squared. So we have 1 minus x squared over k squared, exactly what we have in the representation of the trigonometric function of sine of pi x as an infinite product. So how do we manufacture this product using this material? Well, we simply use this infinite product to the left-hand side of the equal sign, and then we move the sine of pi of x into the denominator of the right-hand side, and this is what we have. 1 divided by x, this is 1 divided by x, times pi x divided by sine of pi times x. 1 copy of x in the denominator, 1 copy in the x in the numerator, cancel each other out, and voila, we have our pi over sine of pi times x. And this is the so-called reflection formula for the gamma function. In this case, obviously, sine cannot be 0 because it's in the denominator, and the zeros of this function are delivered by all integral values of x. So we exclude those values for all x non-integral. This reflection formula holds. And one more thing, I mean, we're coming up on 2 hours, but this is just a little bit of arithmetic fun for you. If we put x equal to 0, if x is equal to not 0, 1/2, if x is equal to 1/2, let's put it this way, if x is equal to 1/2, then in this formula, what do we have? Gamma of 1/2 times gamma of 1/2, this is gamma squared of 1/2, sine of pi over 2 is 1. Here we have our pi, so what do we see? We quickly deduce that gamma of 1/2 is equal to square root of pi. We know this value from here, and because there is another way to represent the gamma function as an integral, we can actually slug in an integral over here and compute the value of certain improper integral as the square root of pi. But for now, this is it for the mathematical problem S2M20, and we will move on to a new challenge next. Our next challenge will be the problem in mathematics S3M21, and the objective of this problem, or the objective of this challenge, is to use the squeeze theorem, or whatever this theorem is called in your country, the sandwich theorem or something else, in order to evaluate the following improper integral from 0 to positive infinity e raised to the power minus x squared, where the integration is carried out over the variable dx. Evaluate this integral, and this is it for this episode. Thank you very much for watching. Thank you for your time. I will see you in the next episode, in which I will present my solution of the mathematical problem S3M21.